is driven by is a complex and a connected physical and chemical phenomena that includes a variety of spheres, as you can see, which is the atmosphere, hydrosphere, cryosphere, and the biosphere. And the energy to the Earth atmosphere system comes only from the sun. So any of the changes in any of these spheres is going to impact the Earth, its climate. So today we will focus on one of the species that is undergoing changes and or that has undergone changes, and what does the future hold? What are the changes that this species gain to the climate, and what is it that we have done or what has been going on in order to remedy this problem? So the other thing that we talk famously is the radiation budget, Earth atmosphere radiation. So what we are receiving from the sun is about 340 watt per meter square. And what is going back up is 107 and 235, which is same as what we are receiving. So the immediate question is, what is the problem? But the point is that whatever we are receiving is actually not going back up. Exactly. That is the reason for what we call as the global warming and also the climate change. So before we go into the description of climate change and global warming, the role ozone plays, let us just look at the atmosphere and the radiative properties of it. As I said initially, that the solar energy is the energy with which the Earth atmosphere system runs or survives. Radiation that we receive from the sun is divided into various, named in different ways, and the entire wavelength region from 1000 nanometer, which is 1 billionth of a meter, 10 to the power of minus 9 meter, from 200 to 5000 nanometers, it's actually called the short wave or the solar wavelength region. And we further divide this into several names, namely the radiation that is in the beginning between 200 to 400 nanometers is called as the ultraviolet, which is the focus just today in today's talk. And the radiation beyond 400 nanometer to 700 nanometer is called as the visible wavelength, starting from the famous violet, indigo, blue, going all the way up, right? And radiation that is more than 700 nanometer in the regime of 200 to 5000 nanometer is named as the infrared. The radiation that we receive from the sun is scattered and absorbed by several species that are present in the atmosphere, including the ozone particles, the ozone gases, carbon dioxide, oxygen, methane, nitrous oxide, dust particles, and also the air molecules. And on the x-axis, you see that the species which are of interest, which absorb and scatter, they are not doing it throughout the wavelength regime, but they have kind of peaks, absorption bands or the scattering bands when they perform the act of absorption and scattering, which is shown. But this is just to illustrate the fact that the radiation that we receive is absorbed by very many species that are present in the atmosphere. So what is seen in brown or shown in brown is at the top of the atmosphere. What we get at the surface is you can see that there is a reduction because of the absorption and scattering by the gases that are present in the atmosphere, including the what type of carbon dioxide, methane, nitrous oxide, ozone. Now, coming back to connecting the radiation that we are receiving and then we call as the global warming. So there is a distinct difference between what we call as the greenhouse effect versus global warming. So the greenhouse effect, which is a natural phenomenon, is the warming of the Earth's atmosphere due to the presence of background greenhouse gases, meaning water vapor, carbon dioxide, methane, ozone, nitrous oxide, right, which trap the radiation is emitted from the Earth's surface and makes the Earth a livable planet. Suppose in this case, if the absorption by these gases did not happen or had not happened, then the surface temperature would be about minus 18 degrees centigrade, cold to support life. And this is called as the greenhouse effect. But we know that these very gases which continue to give the greenhouse, provide us the greenhouse effect, the concentration of these gases, namely carbon dioxide, for example, primarily, followed by methane and nitrous oxide, they are all increasing since the last 300 to 400 years. And that increase in the greenhouse gases is contributing to the difference in the energy that was, or the radiation that was coming in and going out, upsetting the balance between what was coming in and what was going out. That upset or the imbalance is what is called as the global warming. And it is attributed to the increase in the Earth's temperature above the natural greenhouse effect, because of which the temperature is increasing. The man-made greenhouse gases, ozone and the aerosols, which are solid or the liquid particles that are suspended in the medium of air. So, coming to ozone and its importance, for example, ozone is primarily found in two regions of the atmosphere. We saw in the initial transparency, that initial slide, that the atmosphere goes all the way up to 1,000 kilometers or so. Ozone is primarily found in these two regions which are near to the Earth's surface. And even in these two spheres, 90% of the ozone is found in the stratosphere, only 10% is present in the troposphere, the region where we live. And this is the general typical distribution of the ozone that is present in the atmosphere. There is some amount of ozone here, and there is some here, and then when you go to the stratosphere, there is a large increase. Number of ozone molecules that are present in the atmosphere. Now, even there, the ozone that is present, is very high in the stratosphere when compared. Okay? But if you look at the overall composition, the relative abundance of ozone is low. Even in the stratosphere, when 90% of ozone is present, there are only 10,000 ozone molecules. For every 1 billion air molecules, which means there will be 10,000 in 10 to the power of 9 air molecules. 10,000 ozone, so it is that much of a lesser contribution. And in troposphere, it's only 100. So orders of magnitude lower than compared to the stratosphere. So, if you are given a chance, the method to actually condense all the ozone into a thin sheet of layer that is actually the layer that covers the Earth from the ultraviolet radiation, then it will be only 3 millimeter thick, which is the size of the new 1 rupee coin that you have in your. And I also pointed out that the amount of ozone that is present in the atmosphere is significantly less when compared to the air molecules, and that is clear from this description. When you condense all the ozone molecules in the atmosphere, and then per unit area, you will get roughly about 8 into 10 to the power 18 molecules per second. When compared to this, the air density, you take all the air molecules in the atmosphere, the droplets, then you try to condense them, then you will actually end up getting 10 to the power 25 molecules per second. There is a difference of about at least 7 orders of magnitude. The ozone concentration is lower than the air density.
Yes.
However, you know that ozone is very important because of 2-3 primary reasons. One is it absorbs the biologically harmful ultraviolet radiation, sun, and because of this beneficial role, the ozone that is present in the stratosphere is known as the good ozone, while ozone that is produced or emitted at the surface is known as the bad ozone, because it is produced due to the pollutants that are generated from the industrial vehicular emissions. Now, why are we worried about whether ozone is decreasing or increasing? So, the human exposure to, in case of
आपको
reduction
किसके
in
रिगार्डिंग में
the
कॉल किया ये मेरे को पता नहीं चल रहा। मैं
stratospheric
हार्दिक
ozone,
पटेल
and
गुजरात
because
से
of
बात कर
which
रहा हूँ।
more ultraviolet biologically active radiation reaching the Earth's surface
हाँ
increases the risk of skin cancer,
नहीं नहीं सर, हमको
cataracts,
किसी ब्रांच
and
नहीं है,
suppress
हमारा
the
तो
immune
सोलर का
system,
काम है सर।
damage terrestrial plant life,
हाँ
organisms, and aquatic ecosystems. So, to put it in the current trend, the social trending media, so ozone that is above us is actually a very happy sign, while ozone that is near us in the troposphere is actually bad because this is produced due to the pollution that is emitted from the industrial and vehicular emissions. Now, there is another confusion or kind of a dilemma whether to say that is ozone greenhouse gas. The answer is yes, ozone is a greenhouse gas both in the troposphere and the stratosphere because it does absorb the infrared radiation that is emitted from the Earth's surface. So it does, ozone does trap heat in the atmosphere. In fact, this heating or the trapping of irradiation by ozone is evident in the temperature increase that you find. The temperature between 8 to 15 kilometers in the lower atmosphere is maintained because of this absorption of the infrared radiation by ozone. Now, suppose if the ozone decreases in the stratosphere, then it will actually lead to surface cooling, while increase in the ozone in the troposphere will lead to warming. In addition, ozone is important because it is a key ingredient that initiates chemical reactions in the Earth's atmosphere and resulting in chemical cleansing of the atmosphere of various pollutants, namely carbon monoxide, which is harmful, which is again emitted from the tailpipes of vehicles, industrial emissions, etc. The nitrogen dioxide, hydrogen oxides, again harmful, and methane is emitted from natural and the man-made sources. Now, these gases, suppose the ozone is not present, will accumulate to harmful levels, and because of their radiative properties, can actually exert a more stronger influence on life. As a result, any increase or decrease in ozone, be it in stratosphere much above our head or in the troposphere, which is very nearby, induces or it affects the climate, thereby establishing a link, a direct link in changes in ozone to climate. So, how is ozone produced? What is the source of ozone in the atmosphere? Ozone is actually a naturally occurring gas that is produced mainly in the tropical upper stratosphere through pure oxygen photochemistry. So, first the oxygen molecules get split up into two oxygen atoms, and then which again recombines to form the ozone with the wavelength of radiation that is lower than 242 nanometer, which is in the ultraviolet. So, once it is produced, so please note there are two important points here. One is it is produced in the upper stratosphere and in the tropics. Once it is produced in the tropics, how is ozone found? The other groups? The contribution of the production is maximum in the tropics because the amount of solar radiation that we receive in the tropics is higher than what we receive in the mid and the high altitudes. And the oxygen molecules then interact with this radiation, which break up and then form the ozone. Hence, the amount of ozone that is produced in the tropical upper stratosphere is more. Once it is produced, because of the transport of the winds that take away from the species that is produced, this is actually transported. The ozone that is produced in the tropics is transported across the other regions of the world. So this ozone that is produced in the tropical stratosphere, it goes up and then gets moved to the other regions and then it sinks over these particular latitudes, namely the higher. And we will see as the lecture progresses that what is happening over Antarctica when there is ozone is getting depleted or is getting decreased. So it goes up, the ozone that is produced here travels all the way to both the hemispheres, but then you see that there are conditions that exist that actually decrease the ozone at high values. So how does it look across the globe as a function of season and time, and also as a function of the latitude and longitude? So what you are seeing here is actually the scale is from and it is the total ozone that is present is represented here, which is in the name of what is called as the Dobson unit. This is in honor of memory of scientists who actually developed an instrument to measure the ozone concentration. And in memory of these, as it is normal in the science organs of the science community, to name the parameter of the instrument that was discovered. Scientists who did this, for example, the scattering by air molecules is named after Rayleigh or Lord Rayleigh, who found this. And mainly, for example, the Indian, so CV Roman effect, etc. In the same way, it is the unit with which we use to measure the total column of ozone is named after Dobson. And here what you see is the global map of the total ozone that is present in the atmosphere during different seasons. So what is immediately clear is that ozone does exhibit latitude, longitude, seasonal and zonal variations, and it will also exhibit interannular variations, as we will see in the subsequent period of the talk. Now, why it should exhibit geographical variations? Now, this is because of the variations of the air motions and the mixing of the ozone that is produced in the top of the stratosphere getting transferred or transported to the other regions, etc. And also the changes in the balance of chemical production and loss of ozone as air gets transferred. So typically the residence time of ozone varies from a few hours in lower altitude to about weeks to months in the stratosphere, in the lower and upper stratosphere. So the balance of ozone, the amount of ozone that is present in the atmosphere is actually maintained by a balance between the production and loss, which depends on the amount of sunlight that is available, is present. So, okay, ozone is produced now. How does it get depleted? Why ozone should increase or deplete? So, the principal steps that are involved in the depletion of stratospheric ozone this occurs because of the halogen source gases that are emitted at the Earth's surface by human activities and natural causes. You will see the bifurcation of natural and man-made causes, these halogen source gases. So these gases accumulate in the atmosphere and they are distributed throughout the lower atmosphere by winds and the air motions. Now, can they get removed here? I mean, like, for example, rain coming in and then taking away these gases? The answer is most of it, they have very long lifetimes. Chlorofluorocarbons that we emitted, which are being used in a variety of industries, including refrigeration, shipbuilding, foam, construction, etc. So they all have lifetimes depending on which species they are. They have lifetimes of around 60 years. Yeah. So, and these are chemically inert. Chemically, they don't react in the lower altitude. These are heavier than air, but they get transported across to the higher altitudes by the circulation, both in terms of vertical as well as in the latitudinal. Once they reach the stratosphere, they get converted into what is called as the reactive halogen gases. This occurs with chemical reactions that involve ultraviolet radiation. Once they become reactive halogen gases, they deplete ozone. in all regions of the globe except at tropical latitudes because of the production of the source region and the production of the loss and production overwhelms the loss. So the loss in ozone is actually not significant, meaning between 20 degrees south to Earth's ends. So in addition, there is one more phenomenon which we will see in the next few slides. There is a what we call here, we are familiar with clouds that represent the atmosphere, which you can see outside the windows, which are like cumulus, stratocumulus, nimbus, etc. But in the polar regions, there is another phenomenon called polar stratospheric clouds that occur in the altitude regimes. They occur at very particular conditions, very particular time frame. When all the conditions are favorable, they actually contribute to the decrease in the ozone. Now, once they are there, I said these are long lifetimes now. So how they get removed? Once after the depletion is over, after so many years or so, they actually will start descending down to the Earth's atmosphere, and where they get moved by the air from the moisture. Now, how was ozone in the past? So let us go back by 60, 70 years from now. You see that this is in the southern hemisphere. We'll also see later northern hemisphere over. So the scale is the same in Dobson unit. Color is also the same. It is varying from 100 to 60. So this is Antarctica. What you are seeing is actually the continent of Antarctica. And from the year 1970, so you can see that the more reddish hue slide is seen by the 1979. Now you see that the entire continent of Antarctica is actually having ozone that is much lesser than 200 Dobson units. Please coordinate the color scale. You will see that what was there in green here, which was the excess of about 300 Dobson unit ago. Now the scenario is the same even now in 2020, which you will see in the next 2 or 3 slides. So there is a huge decrease in the ozone is present over here. And please note that decrease is not only restricted to Antarctica, but also the regions surrounding Antarctica, which is much bigger, as you can see this figure. Now, so I mentioned that there are halogen source gases that contribute, they get converted to reactive halogen gases, and then see that these are the amount of halogen source gases that enter the atmosphere. On the left column is the total chlorine amount, is present in parts per trillion, 1 in 10 to the power 12. So these are these gases or the concentrations of these are very, very small when compared to, let us say, air molecules or even ozone, for example. But the kind of damage that these gases do to the human life, its existence is tremendous, orders of magnitude high. So these are produced by both natural and the man-made sources, human activity contributing much significantly. And you are also seeing, for example, the changes between 93 to 2016. Why 93? Because that was when the chlorine concentrations in the Earth's atmosphere peaked. With respect to that, the implementation of the Vienna Convention, Montreal Protocol to use the chlorofluorocarbon substances that deplete ozone, etc. There have been changes, there have been reductions, but still the concentration is significantly high now. So is there a change between natural? You don't see much of a change, but you see that there are these gases that are present in the atmosphere, depending on their lifetimes. Yes, there is a reduction percentages. It is the same with respect to bromine also. So when we say chlorofluorocarbons, we are referring to the chlorine, bromine, and iodine substances or the compounds that combine to form what is called as in total the chlorofluorocarbons. So if you look at the total chlorine, the scales are here. With respect to bromine, chlorine is roughly about 150 times more. So the fluorofluorocarbons that are present in the atmosphere are actually the most abundant ones are the chlorine-containing gases. But in terms of the depleting potentials, bromine will be much higher compared to fluorine. So this is again illustrated here. The kind of halogen source gases with the chemical reactions that occur with the amount of sunlight, ultraviolet sunlight is available. They get converted into reactive halogen gases, and these reactions they occur on the stratospheric clouds, which we'll see next. And then they get converted into reservoir forms of reactive chlorine gases such as ClO and O2, hydrogen. And then the most reactive form of this is ClO, which is very, very efficient in chlorine chloride, which is very efficient in depleting ozone. So one of the cycles I am showing here. So we saw that the ozone molecule is produced by the reaction involving oxygen molecule. Ozone gets produced, and this chlorine monoxide, ClO, which is a reactive form of ClO and O2 of converted because of the from the halogen source gases to the reactive gas. They can in this reaction you can see what is destroyed is so the ozone that is produced by oxygen molecules in the atom gets depleted because of the chlorine monoxide is in this fashion. And please note that I have named this as the chlorine catalytic cycle because in the whole reaction, chlorine does not get destroyed. It survives as a catalyst and then can keep continuing to deplete ozone till it loses certain amount of energy, come back in the lower atmosphere and then gaining the energy, go back up and then start to deplete ozone. That is why the species that are already in the atmosphere, because of their non-resonance factor, because of this catalytic process, they can deplete ozone long after even production has stopped. So I did mention about the clouds that form in the higher latitudes, namely the polar regions, which we call as the polar stratospheric clouds, which is nothing but the nitric acid, HNO3 and the water which condense on the pre-existing sulfur-containing particles. So these sulfur-containing particles are nothing but familiar aerosols, solid or liquid particles. But in terms of the number, it is very, very small. The number of sulfur particles in those altitudes. The temperatures in the polar regions are much lower, meaning minus 78 degrees centigrade, which is in terms of Kelvin is 195. So if you look at, so this is one example of how the polar stratospheric clouds look in the polar regions, which looks definitely different than the clouds that we are right now seeing across our window in the lower altitudes. So what we are seeing is the variation in the temperature in May to October in terms of the Antarctic, this is the southern hemisphere, and between November to April, Arctic, which is the northern hemisphere. And what we are looking at is the range of temperature, the temperature values, those were measured during the last 50 years for both these regions, mainly the Antarctic or the Arctic. So the black perpendicular line that you see represents the temperature of minus 78 degrees. Which the meaning values that are lower than minus 78 polar stratospheric clouds will form. These are the perfect conditions for polar stratospheric clouds to form in these latitude regions, high poles. And so here we are seeing graphs in blue color represented by the shade, okay, and also the line in red with the yellow shading. So the blue one represents the Antarctic temperatures, the red one represents the Arctic temperatures. This time frame when the ozone gets depleted in both the hemispheres, but in different times. So it is immediately clear that temperature can be lower than minus 78 degrees over Antarctic for more than 6 months a year. See that these values are lower than minus 7. But in the Arctic, it is not that severe. The temperatures are lower only for months here during the Arctic. Keep that in mind as the top process. So, when does first let us begin with Antarctic ozone hole and then we move on to Arctic. Why it is called a hole, I will describe it in the next few minutes. So, for example, what you are seeing here is the conditions in May, particular year, at around 18 kilometer altitude, which is the region where the ozone is depleted. So, the color bar is the same that you are familiar with. Here you see that the ozone abundances. Here, in terms of the abundances, we are now seeing. So here, so I'm now concentrating on the left, which is the Antarctic is shown in the black curve here. You see the ozone values are way high, which is red. This is in May 2000, May of the year, particularly. You see the temperatures are on the order of about minus 60 centigrade, which means that it is still not temperatures that are good enough to form the polar surface clouds. And you also see hydrogen chloride that is high, but then that does not become the reactant to deplete ozone. Nitric oxide is also high, chlorine monoxide is very, very low. It's all entirely purple. It is all low concentrations. Now contrast this with September, in the day, like today, for example. You look at it, we are looking at, imagine that this is a scenario that was yesterday over the Antarctic. So, you see that first black curve is actually behind purple, where the ozone concentrations have decreased enormously from what it was to here. So, from about 280,000 parts per billion volume of ozone, it's now become almost less than even 18. About 1,000 parts per billion ozone molecules decrease. Now, look at the temperature, which is much lower than minus 6 centigrade we saw. And then you also look at the chlorine monoxide concentration. These have increased hugely from nothing to maximum scale. Now, why? The immediate question is, why does it occur only for Antarctica? Why doesn't it happen in other places? So, we know the timing that this will occur in late winter and early spring. The abundant reactive halogen gases there, and then the temperatures are low enough to form the polar stratospheric clouds, and the air that is present over the other air that is present in the atmosphere, which we call is a kind of a vortex. So I imagine that this region is actually kind of bottled up. In a bottle, you have this air, and that contains large amount of these chlorofluorocarbons. And then once the sunlight is to form, as we know that it is 6 months of darkness, so once the sunlight starts falling on the Antarctic, all these conditions, including the polar vortex, helps making the ozone depletion reactions faster, and you can see the change that happens for this Antarctic. Now, coming to the present, as of today, this year, what has happened to the conditions of ozone in the Arctic? So far we looked at, for example, the 50 years of change and the conditions of change that are required ozone in the Antarctic. And now coming to the present year, 11 June 2020 to 11 September. 3 months time, you can see that the ozone is the same color coding. You can see that there is a huge decrease in ozone that is present over the Antarctic, and you can also see the white continental map. So, what has happened? How does it change day-to-day basis during this particular year. So to begin with, in July, so this what you are seeing is the ozone hole area, which we'll talk about in the next transparency. In the area where the ozone values are lower than 250 thousand, why 220? I will tell you. So now, when the ozone decreases, so from in July, it started in July, July 1st, the ozone there was no depletion, meaning, so that is why it is represented as 0. And then as you come across, going all the way up to September, for example, see that the area in terms of millions of square kilometers, it has increased, this is 24 million square kilometers. Compared to the size of the Antarctic continent, this is even much larger. So how much the ozone has decreased from the value of 233 in July to now, this is roughly 141,000. So you can see the huge decrease in the ozone value as we saw previous transparency. So what about the stratospheric temperature for the polar stratospheric clouds? The temperatures were to begin with, so we said that under 95 Kelvin is the main value for the stratospheric clouds. You can see that the values were lower, and then they start decreasing. Once later in October and November and all, they will the temperatures will increase, and so the ozone depletion will also come down, as you can see. The values, the white curve and the gray shaded curves indicate the averages of the increase in the ozone the last 50 years or so, starting from 1980. So the ozone, for example, we looked at how the ozone hole or the depletion is much higher than even the size of the Antarctic continent, which is now, this is actually about 25 million square kilometers. That is roughly twice the size of the Antarctic. And we call this as ozone hole and not say decrease or depletion or decrement or something. We call specifically this as ozone hole. That is because if you look at the ozone values from high above, and you look at the concentration or plot the concentration on the globe, you will see that the ozone values increase as you go over the Antarctic continent, and it will actually look like a hole in the concentration, and that is why the increase in ozone over the Antarctic is called as the Antarctic ozone hole. And what is the value that corresponds to the called as the ozone hole? It is when the ozone concentration in Thompson unit is lower than 220, then that is actually called as the ozone hole. Now, the immediate question is, we talked about Antarctic, and we also said that, well, it happens in the Arctic also. So, is there a comparison? Is the same thing happening in the Antarctic? Let us look at the difference between Antarctic and the Arctic. So, for example, on the first panel, you see as a function of the altitude, the ozone concentrations. The initial in 62 to 1971, with the same measurement method, flying balloon to measure the ozone concentrations. See that this was the concentration in 1970. But now look at the recent last 30 years or so, the ozone from blue, green, is nothing, almost everything has been washed out. Kind of decrease is very significant. And among these years, look at the lowest that was ever measured. Look at the curve in red, which is on 9th October 2006. You don't see any ozone at all over the Antarctic. This is almost zero. Now, look at contrast this with the Arctic, for example. Ozone has depleted with respect to the last 50 years or so, but then the depletion is not as significant as you see in Antarctic. Now, why is it that there is a difference? I mean, same pole, one is located in the southern hemisphere, the other is located in the northern hemisphere. The ozone gets transported, the temperature both are cold, temperatures are lower, etc. Now, the question is, there is a fundamental difference between the amount of ozone that is present over the Arctic and the Antarctic. The average level of ozone in the Arctic is higher than what is found in the Antarctic. So if you look at the average levels of ozone in the Arctic, this is on the order of about 450 parts per billion by volume, while in Antarctic it is less than 300. So when you compare the values, so the Arctic values are inherently higher than what you have in Antarctic. Now, the other change that occurs in the northern hemisphere, said ozone is produced and it gets transported and all that. So the ozone gets transported to higher altitudes, then which goes to the higher latitudes and then sink the high latitude polar regions. Now, forward and the downward transport of ozone which have stronger in the northern hemisphere when compared to the southern hemisphere. So the amount of ozone that is present in the northern hemisphere is higher than what's which is in the southern hemisphere. Now, the other, so we talked about polar stratospheric clouds and the particles that are present in the atmosphere can actually decrease the ozone. So, what is called as the heterogeneous chemistry, because the species that are involved includes gases. These reactions of ozone depletion occur on the solid or the liquid particle, which is the sulfate particles that is present, and then which produce chlorine, the highly reactive species, namely the chlorine and the nitric acid, which then also result in the active form of chlorine, reactive form of chlorine, namely chlorine monoxide, and then ozone depletion takes place. So whenever there is a volcanic eruption that occurs, the ozone depletion will also occur. As you can see here, for example, there are two natural causes that could contribute to change in ozone. One is the incoming solar radiation itself, which is the prime driver of the solar system, and the other one, natural cause, is the volcanic eruption. So what you are seeing in the top is the incoming solar radiation for the past 60 years or so, follows a 11-year-old seasonal cycle, as you are all familiar, changes of cyclic, which is solar maximum, solar minimum. And you see the cyclic periodicity of the solar radiation. Compare this with the decrease in ozone that we have seen in the last 60 years. Now, you can see that these changes cannot accommodate for the decreases. Is what you see as the global ozone changes. Now, what is plotted here is the change in the concentration due to the volcanic eruptions in the last 60 years. So these values are zero. Any dips indicate increase in the amount of aerosol particles due to volcanic eruption. See that these are also kind of happening in once in about 10 years in the last 40 years, and none of them are able to account the gradual decrease that is happening. So if there is a volcanic eruption and the aerosols that are produced as a result of the volcanic eruption, ozone will deplete. As you can see here, as it happened just after the last eruption, which was Mount Pinatubo in 1991. But however, the gradual decrease is actually not being explained by both natural causes of variation, which is the cyclic variations in the solar radiation and also the volcanic. This can only be explained by the abundance of the chlorine and the bromine molecules or the species that are present, which is represented here in terms of the equivalent effective stratospheric chlorine. So what you can see is an entirely anti-correlation. The depletion in ozone corresponds to the increase in these gases. Then ozone will try to become better as soon as the concentrations of these. So the long-term increase or the change in ozone can only be attributed the increases in the chlorine and the bromine substances that are present in the atmosphere over the same time period. So, is the ozone depletion global? The answer is yes. But however, in the tropical latitudes, as I mentioned earlier, the changes are very less when compared to what is happening in the higher, both the high latitudes, namely the southern and the northern. Now, one of the effects is one of the participants now asked a question as to the ozone anyway is decreasing in the high latitude, so why does it concern us? So this can, as we know that the reduction in ozone can contribute to the increase in the ultraviolet radiation. That can, so the observations do indicate that the surface level ultraviolet radiation has increased. So our exposure to the ultraviolet biology will be active radiation has increased, leading to erythemal, which is the sun burning issues. And the surface level ultraviolet radiation has actually increased in the last 40 years. The clouds and aerosols, clouds that are present here in the aerosol particles, can offset the increase. However, if you take the total summation, still the average change is still negative, not negative. This can, the cloud and the aerosols can only change a little bit. So on an overall sense, it's still facing the effect of decreasing the ozone. So the immediate question is whether with all this reduction, when is it get to the future, which will be the same as the past in the last 40 years or so. The ozone concentrations, when it will come back up. So these are some of the estimates, observations, projections of the gases that ozone. So as you can see that all these gases are all in parts per trillion, and then the abundances were increasing in the last decade, and now they have started showing decreases. The turnaround happening around 90. So, and then these are projections that they will actually reach the levels 60 to 80. So these are as far as the man-made contributions and emissions that happen and the changes that we occur. These are. Now, the ozone hole, for example, is it uniform that will occur every year at this time with the same magnitude continuing to happen every year? The answer is actually yes or no. So what you are looking at is the ozone hole over the Antarctic during 2 years, 2001 and 2003. They look more or less similar. Now, what happened in between the year 2002 is very starkly different than the years preceding and succeeding years. So, what happened was initially the hole was circular, but then it got split into two depleted regions. So, you can see that, for example, here the whole Antarctic there was a blue shade, but here in 2002 you don't see this. Now, this was caused by warming of the polar stratosphere, which is actually detrimental or acts against for the formation of the polar stratosphere clouds due to the meteorological disturbances of the variations that originated in the troposphere at mid-latitude. So the air in the mid-latitudes get transported to high latitudes. This actually was warmer, and then it tries to decrease the temperature, thereby increasing the polar stratosphere. So warmer temperatures will reduce ozone depletion, meaning the loss is less, as it happened in 2002 compared to 2001 and 2003. This variability in the ozone depletion is entirely attributed to the natural causes, which is the change in the dynamical ecological systems. Now, coming to the ozone that is near Earth's surface, namely stratosphere, we know that it occurs through oxygen photochemistry, while in the troposphere, this occurs due to what we call as the bad ozone. It occurs due to, it is not directly emitted into the air. It is created by chemical reactions between the various oxides and the volatile organic compounds in the presence of heat and sunlight. From where these nitrogen oxides and volatile organic compounds come is of industrial facilities, electric facilities, vehicles, gasoline, chemical solvents, which are all the forms of urbanization and globalization, which increase the resulting in the vehicular industrial emissions, also resulting in smog conditions. So, if you look at the forcing, the changes in the ozone. For example, we are all familiar with changes in the carbon dioxide and the warming that it is using, as we saw in the initial few slides. See that this is all highly positive, going all the way up to 2 watt per meter square. But ozone increases in the lower atmosphere